Good day everyone, my name is Olivier Sperandio and I will be presenting our last development on iPPI-DB and the way we use MarvinJS and the JChem library from Chemaxon to support the development of a new web application for iPPI-DB, or database of protein-protein interaction modulators. First, I would like to thank the organizer, Chemaxon, for giving me the opportunity to present this work and present you the way we use their solutions in a way to support our own project in this database. I will start by briefly give you an introduction on protein-protein interaction, as they are at the core of this project and at the core of this database, iPPI-DB, and present the last development using Chemaxon solutions. And I will finish by giving you some future directions and the way we want to pursue this project later on. First, why studying protein-protein interaction? In the field of drug discovery, they represent a wealth of potential therapeutic targets with numerous implications in nearly all cellular compartments and various pathologies, with a special interest in infectious disease because of the host pathogen interactions. These days, we're talking a lot about the coronavirus and this interaction between the human receptor ACE2 with the spike protein of the coronavirus. Obviously, this interaction represents a key leverage in terms of pharmacological modulation to prevent the viral entry into human cells. And more generally, these interactions represent very interesting options in terms of drug discovery. Yet, the development of non-peptide molecular weight compounds as a source of new drugs targeting PPIs is still a major and difficult task, as exemplified by significantly lower hit rates observed during experimental screenings or high false positive rates. There is a couple of reasons for that. First, not all PPIs are meant to become targets, as in therapeutic targets. Second, not all PPI targets are equally suited for small molecule modulation. Some may require the development of larger peptides or biologics or monoclonal antibodies, for example. And the second main reason for these difficulties in targeting PPIs for small molecule drugs is the nature of the chemical libraries that have been historically used on those systems. So clearly there is an aspect concerning the PPI target, its selection, its location and the biological networks, its structure, its dynamic, the presence or not of druggable binding cavities within it. And another aspect concerning a small compound, the chemical space, the presence of or the existence of privileged substructure and the nature of the small compound that are used to identify initial quality chemical probes. And the purpose of iPPI-DB is to provide the community with tools to better calibrate the type of compound that should be used for this purpose. Behind this project, behind the iPPI-DB initiative, there is this scientific concept that we should learn and be inspired by success stories, both in terms of the small compound that modulate PPI targets and in terms of the target itself. Obviously, the chemical structure of those compounds contain information, valuable information that we could learn from and try to make sense of why and how those compounds are capable of modulating such intricate targets. Now, in terms of chemoinformatics strategies, it's always interesting to gather a set of compounds, positive data set, let's say iPPI on one side, inhibitors of protein-protein interaction, and non-iPPI on the other side, to try to understand what makes those compounds so special through a machine learning process, for example, and try to build models and gain knowledge about the physical chemical properties that explain why such compound can modulate PPI targets. So this is the very purpose of the iPPI-DB database, to help medicinal chemists and chemoinformatics as a community to better design new drugs to target protein-protein interactions. Historically, iPPI-DB has been always focusing on the collection, the manual collection from the literature, either PubMed article or world patents, of chemical compound with the capacity of modulating protein-protein interaction by favoring quality data both for the compound and the targets. We have made already 2 publications, one in drug discovery today and one in nucleic acid research. And this project is now almost 10 years old, and from the beginning we have the support of the Chemaxon product, and we are very thankful for that, because using MarvinJS and the JChem library, we combine those tools to other tools and provide web-assisted tools to provide a community with this database and this querying tool to help the community to better design the future generation of iPPI compounds. I'll be talking about 2 aspects today in terms of a new design of the web application. One aspect concerning the querying, the new querying capacity of the database, and the other concerning the maintenance, which is a major breakthrough for us, because we will preserve manual maintenance, but we have sort of a crowdsourcing tool, but it's API assisted now using MarvinJS and JChem tools. I will start with the web application for querying. So here's the new design of this web application. So you have several tabs. The first tab is actually the About tab, from which you can find statistics about the compound. You can see that you have like several hundred iPPI compounds, several dozens of targets, binding assays, either cellular assays or biochemical assay, and more than 150 bibliographic sources at the moment. You can see also some statistics about the physical-chemical distribution of the compounds. Those distributions are made possible because we use the JChem library to calculate some key physical-chemical properties that are usually employed to depict drug likeness of the compound. So once you are go to the Query Compound tab, you right away have a list of thumbnails describing all the structures we have within iPPI-DB, and on the top left you can see that you have this blue button, Open Filters, from which you have a list of different criteria you can use and make your own selection of compounds. Here are the ligand efficiency criteria. You can have put your own threshold you have selected. You can add other criteria, such as the compliance of the compound with some chemistry rules, such as the Lipinski rule of 5. You can select obviously the targets you're interested in, let's say MDM2P53 interaction, which has been extensively studied at the pharmacological level, and then select a specific type of test, let's say a cellular test, for example. And then you can switch to the table view, from which you can activate or deactivate specific column here, activity, ligand and lipophilic efficiencies. Once those columns are activated, you can use them to sort the data and finalize your selection and select a given compound which has its own ID card. Here, compound 338. The first tab of the ID compound tab is providing a list of names and external link to external database, such as the PubChem database or the PubMed database from which the article was retrieved. And then you can switch to the physical chemistry tab, from which you have the compliance with some chemistry rules, Lipinski rules, Weber rules, Pfizer 375 rules. Also a radar chart displaying the main physical-chemical properties of the compound with respect to a reference drug-like compound here in blue. And you can consult the value of your own compound on this radar chart. And at the bottom of the page, you can see actually you can visualize the chemical space of the whole iPPI-DB database, see your actual compound in reference to that. It is based on the principal component analysis that is usually employed to depict chemical space. This plot is interactive. Each point is a molecule. You can click on the molecule and go to its own ID card and consult iteratively all those information, one compound at a time. Then you can switch to the pharmacological tab, on which the main activities are summarized. And here you have an efficiency plot, ligand efficiency versus lipophilic efficiency. And again, this plot is interactive, so you can click, see the structure, and click on the structure to go to its own ID card and navigate through the efficiency plot, the same way you can navigate through the chemical space plot. And here you have a summary of the main activity available within iPPI-DB database for each compound. Here you have 4 binding affinity available on this compound. So now you're interested in the drug likeness of compound 338. You can see to what extent it looks like some under development or approved drugs from the drug bank using a Tanimoto index. And you can click on the link of the most similar compound to 338 and then go to the drug bank and have access to the wealth of information that is available from the drug bank website. So let's say you're interested in this compound 338 after navigating its own ID card. You can copy and paste its canonical smile from the web page and actually paste the canonical smile into the chemical similarity filter and look for all the similar compound to 338 within iPPI-DB using the MarvinJS application. But obviously you can do that even if the initial compound is not from iPPI-DB, and you can consult the list of similar compound in decreasing order with respect to the Tanimoto index of their similarity. This can help you to finalize your selection and make an educated decision in terms of the compounds you found interesting within the database. Obviously, you can export those results as a CSV file if you want to do so. So this is what I had to tell you about the new querying web application of iPPI-DB. So now let's switch to the new web application for maintenance, which is a major breakthrough for us because we are really it's very important for us to maintain this manual curation of the database. It doesn't mean we cannot use API or automated web services at our disposal to support this manual curation. This is actually what we have done. So now you have a contribute tab within the web application. You can log on using your ORCID ID, for example, and you can click on this add content button, and a series of questions will be asked to you to support the maintenance of the database and entering new data. Here you can enter, for example, a DOI, and it would automatically retrieve information for the article. You have to select the type of data that is present in this publication, let's say X-ray data and in vitro study. You provide a PDB code in which a structure of the complex is described and select the type of architecture this complex is made of. Here an hetero-2 dimer AB. This PDB code will be used to retrieve automatically UniProt codes and FAM information about the domains. You can provide name of PPI targets, here bromodomain histone interaction, and an associated disease to this target, here acute myeloid leukemia from the Mondo database. And then you switch to the compound tab, which is a very important aspect. You provide the name of the compound as stated in the publication, a common name if it has one, and a PDB ligand ID if it has one, if it's co-crystallized. And then you can sketch your compound using MarvinJS or copy and paste a smile or a UPAC directly from the inside the window, which is very convenient because most of the time in the articles the structural data of the compound are provided as UPAC codes. And then you switch to the activity test, here a biochemical assay as in the form of a isothermal titration calorimetry. It's binding assay. You have one compound in this test. You can see that it is already listed below the one you have selected and provided in the previous tab, and then you can actually provide information about the type of activity. It's a KD in this case. The value of the activity is 134 nanomolar, and then you can save this entry, the whole entry, within the database, and right away see as a summary the entry you've made to check if everything looks fine and accurate. And once you've done that, you can directly see your result in the database. You can see the structure, you can see your contribution has been taken into account. Although it's not fully validated, the full validation has to be made by a core curator. So this is why you have this orange frame around the structure of the compound. But once the core curator have validated your contribution, it is now fully accessible, and all charts, all plots, all IDs of, for example, with reference to external data banks such as Campbell, such as PubChem, or Tanimoto index with respect to drug bank, for example, everything will be updated automatically and will be available for the whole community to be consulted. So that's what I had to say about the new contribution mode for iPPI-DB. I will switch to future direction very briefly. So our future direction concerned consideration of the target itself. We will soon consider the 3D structure of the targets, from which we can retrieve a lot of very important information. We'll offer better functionalities to mine information and better cross-reference target and compound information. I would like to thank everybody involved in this project, from my previous lab and from my new lab at Institut Pasteur in the unit of Professor Mathieu Nilges. And I would like to thank Chemaxon for their support for all those years by providing MarvinJS and the JChem library. And I would like to thank you for your attention and be ready to answer any question.